Hello students, welcome back. Okay, it's time to learn how to make some graphics that are going to be useful for you in interpreting the descriptive statistics about temperature data from various stations around Nebraska. And in order to do that, I'm going to suggest that one of the kind of diagrams you'll want to make is called a histogram. And I just want to help you remember that if you want to make graphics on Chesapeake and view them on your PC or your Mac, you're going to have that X11 connection stuff set up again. Remember we did that, gosh, either back in section 2 or section 3, module 2 or module 3 way back early in the course. You can certainly go back and look up that again. You can certainly let me know anything you need to know about that if you're having trouble. Remember, we test it using that XIs command. If you think you have an X11's connection set up so that graphics can go back and forth between your computer and Chesapeake, then you use that XIs command to see if it's actually working. I think everybody got it working back in, September or something like that, so we should be able to get this to run again. Because we're going to be using Octave and some of the built-in functions in Octave to produce different kinds of diagrams. The first one we're going to do, though, is histograms. And the command to produce a histogram is just hist. It's a pretty useful little command, and in fact there's lots of different ways to use the command. The documentation on the Octave website about the hist command is actually a little bit overwhelming. There's actually kind of a lot of information there about all kinds of different ways you could use the hist command. Let me give you an example here. What if I just put hist and then in parentheses the data that I want to go into the histogram? For example, like let's say I have this array I've called my data, and this my data array has already been filtered, or whatever you want to say. We've done our database operations on there, like our logical indexing and so on, to narrow it down to just the year and the month and the station and so on that we want from our data. We've maybe done the logical indexing in such a way that we've gotten rid of any missing data, things like that, or whatever. So column 5 of my data is just the max temperatures now. So if I say histogram of just this array, all rows column 5, it's just a bunch of numbers. And the hist function will produce a graphics output that is the histogram of this distribution. What I want you to notice, though, is for the histogram function here, there is just one argument, to use the right word here. It only takes one value, just like sine of x. X is the only input, and then sine converts that, does math to make it, the sine operator of x. In the same way, we just have sent it one thing, this list of the data that are going to become, be used to make that diagram there. All the temperatures that we can say, oh, gee, there was only this many of them between -17 and -15, and there were this many between -15 and -13. There's just this one argument. Okay? It happens to be a whole list of numbers, but it's just one argument. This my data column 5, okay, or it could have been column 6, or it could have been something else. But it's just a histogram, just one argument that it produces that histogram. Now, I can look up there at that histogram that it produced on the screen, and I can say, well, that's just charming. I can see that there's sort of a vaguely mound-shaped distribution to, this happens to be max temperatures at some particular station. I don't remember exactly what I was doing when I made this plot. But to understand exactly what just happened, we need to think about what a histogram actually is. I mean, what we did is we took the range of values and we divided that range of values that are observed up into equally sized bins. Bins are the technical term here. So like if these are temperatures, maybe there's a bin from -12 degrees to -10 degrees, and then another bin from -10 to -8, and so on, in these equally sized bins where each one is 2 degrees wide. So we divided the x-axis up into each of these little bins, and then we said that the heights of each of these bars are going to be suggesting how many values there were that correspond to each of those bins. So in this case, I don't know what that would be. Let's say the 25 to 30 bin had the most observations. Let's say there were, about 500 observations of high temperatures that were between 25 and 30 Celsius, and so on. Okay, so once you kind of at a philosophical level like that actually think through what a histogram actually is, what you see is that with the simplest way that we have to create a histogram, where there's just this one argument. Here is a list of numbers. I want you to make a histogram out of them. Notice I didn't tell Octave anything. I didn't tell Octave how many bins to make. I didn't tell Octave how wide the bins should be. I didn't give Octave the range of the data. I didn't tell it anything. So clearly we have somehow triggered some defaults. Somehow or other, if we aren't telling Octave how many bins we want, or we aren't telling Octave what we want is like the beginning and the ending of each of the bins, apparently it has some way of figuring it out. Clearly Octave has some way of, fine, you didn't tell me what to do, I, as an interpreted language, will decide for you how to make it work. By default, Octave has a nifty strategy for figuring out how to make a histogram diagram that makes a diagram that isn't so ugly, but it isn't exactly what you would want it to be. Let me tell you what I'm talking about here. By default, if you don't tell Octave how many bins you want or how wide you want the bins to be or anything, what Octave does is it goes through the list of data that you provided, in this case my data, all rows, column 5, all these max temperatures. It goes through them, it finds the maximum temperature, well, the maximum value for the histogram, and the minimum, okay? So it computes the difference between those two. Technically that would be called the range, right? The difference between the maximum value and the minimum value. And then it divides that range up into 10 equal bins. So whatever that maximum value is, whatever that minimum value is, it takes the difference, divides that by 10, and that's how wide each of those bins will be. So the first bin goes from minimum to minimum plus the quantity, maximum minus minimum divided by 10, all the way up, you know, in the next bin and the next bin, and then it went all the way up to the maximum. That's neat, but those aren't going to be like round numbers, okay? The minimum is not going to be necessarily like a nice round number like 10 or 20 or negative 10 or negative 15 or something. It's going to be whatever it was, negative 11.3. And the maximum is going to be whatever it happens to be, 17.8. Well, then your range is from negative 11.3 to 17.8, and you divide it up into 10 equal pieces, and none of these edges of these bins land on, like, you know, you kind of would like those little ranges to be like 0 to 5 degrees, 5 to 10 degrees. They're not going to be that way by default in Octave. Okay, but it gives you insight into how the diagram actually was made, and it's going to give you insight then into how should I change this diagram so that it is better. I mean, this diagram as it exists now isn't terrible, it's just that we could do better. This is not the best histogram I've ever seen. I mean, like the little bar of the histogram here that I have highlighted in yellow there, I can see that there's some number, let's say about 380 values in this bin, but I don't actually know what this bin is, because it isn't exactly on a round number. It looks like it's from somewhere around, like, the bin is from like 7 to 12 or something, but it's probably not exactly 7 to 12. It's maybe 7.2 to 11.9 or something. It's not that helpful if we don't actually know what these ranges are, or have other ways of controlling them. So fortunately, Octave provides a whole toolkit of ways to make these diagrams look better. And in fact, in some ways it's overwhelming. There's too many ways to make these diagrams look better. But a simple way to kind of get a little more control over the diagram is just to simply provide a second argument to the histogram function. The first argument being, as it was before, the list of numbers that you want to make a histogram out of. You know, like, here's a big table of temperatures, tally them all up for me, histogram function, comma, and then a simple integer number. If you just provide your second argument there as just an integer number, Octave will say, I bet you mean that is the number of bins. So, for example, I got this diagram here by making my histogram command hist, and then in parentheses, 2 arguments, separated by a comma. The first argument is my underscore data, all rows, column 5. Then the comma, because now we're moving on to the second argument, and that second argument is the number of bins I used, and I made this 100. So now there are 100 little bars here across this diagram. 100 little bins have been set up. Again, because I didn't tell Octave anything else, it has decided to just make the lowest bin equal to the minimum in the data set, and the farthest to the right bin on the scale is the maximum of the data, and then it just computed the range between the maximum and the minimum, and then it divided it by this number of bins, which in this case is 100. So we got a whole bunch of little bins here on this diagram here, and we can see that we sure have some insight into these curves that we didn't have before, and into the distribution of these temperature data. It sure looks kind of different than I was expecting. It's kind of interesting to think that the histogram on the left, with 10 bins, and the histogram on the right, which has 100 bins rather, are the same data set. You certainly can see that there are some strange spikes, for example, in the distribution of the data that you couldn't tell when you only had 10 bins. My guess is that some of these some of these stations have a digital thermometer rather than a mercury thermometer, and it's only accurate to like the whole degree or something like that. That'd be my guess as to why we have some spikes there. There's some stations that just keep observing round numbers of temperatures. Anyway, we still aren't really in control very well, though, of this diagram. I mean, this is better. I like the fact that I can at least control the number of bins here. But each individual bin here is still on weird numbers, right? It would be really neat if these bins were like 0 to 1 on the x-axis, then 1 to 2, and then 2 to 3, and so on. But they're not. They are, you know, whatever maximum minus minimum divided by number of bins, that's just where they're falling. Then, you know, minimum plus that bin size, minimum plus 2 times that bin size, etc. They're not round numbers. Okay, so this is still pretty messy, because we're just not really actually in control of these bins very well. Don't get me wrong, there's a whole lot more insight we can get by being in control of these bin sizes, but we need to see if we can come up with something better. Well, another possibility is to put a second argument to our histogram function. Again, you can see how there's 2 arguments separated by comma. The first argument is my data, all rows, all columns, but the second one now is going to be an array. This is an array. I gave it the name bins. It could have been anything, but bins is a good name. Where, look on the line before there, I defined bins as being 20:5:45. Remember how that business of the colon notation of like an array works? It means we're starting at the number -20 and then going as far as the number 45 in increments of 5. So the array bins contains -20, -15, -10, all the way up to 45. It has whatever that works out to, you know, 22 numbers in it that are -20, -15, etc., all the way up. Those numbers then become the centers of each of the bins. So there is a bin centered at -20, a bin centered at -15, a bin, and then, you know, so it spans from like -22 to -22.5 to -17.5. The next one spans from -17.5 to -12.5, and so on, all the way up to one that is centered on 45. Okay, so this certainly gives us, you know, much more control, and again, now I seem to have even, you know, kind of a lovely looking histogram. I'm not quite sure why it's kind of bunched together on the x-axis, but we could find out. I mean, I just don't happen to know why Octave does it that way. If anyone was interested, though, we could probably find out. We're not going to get bogged down. Octave provides all kinds of tools to like put labels on the graph and so on, which, you know, life is short. We can live without like there being labels and keys and so on the diagram at this time. What I would rather show you actually about histograms is how there's a useful trick you can do with the hist function that will be useful for you in terms of finding missing data observations. So here's the deal. Let's just let Octave make a default histogram where it just is going to say, I'm going to make 10 bins. They're going to go from the maximum to the minimum value and so on. Let's actually just do that. Here I'm making a histogram of column 5 of my data, and I get a histogram that looks like this. Does that look normal? That is the weirdest looking histogram I've ever seen. What happened? How come it's just a bar? How come it's not like, you know, some kind of mound or something like that? Well, it actually is a little different than what you think it is. Why is it such a weird histogram? It's because there's missing data. If I haven't already removed all of the -999.9s, what is the minimum of my data? -999.9. So it divided up the range from the minimum, -999.9, to the maximum, whatever it was, let's say 40 Celsius. Well, that's a pretty big range. That's over 1,000 degrees Celsius range. feel free to divide that up into 10 bins. So let's say each of those bins is about 100 degrees Celsius wide. So that first bin, farthest to the right, the tall one there, it probably spans from like negative 60 Celsius to about 40 Celsius. That's about a 100 degrees Celsius span. Well, practically all the observations fell in that range, right? In fact, no observations of temperature were between negative 60 and negative 160, or between negative 160 and negative 260, or negative 260 and negative 360, all the way down until finally between, you know, whatever that would be, like 1,000 and, well, it's actually between the minimum. The farthest left bin would be negative 999.9 to that number plus roughly 100. And there probably was one time there was a negative 999 in there. So that little, you can kind of just barely see, there's a little blue bar there on the farthest left. That's probably one observation. And then there's all the rest of them fell in that range of negative 60 to 40 degrees Celsius. This looks like the world's stupidest histogram, but actually it was hugely useful because it helped you realize you didn't get rid of all the missing data yet. There's still one in there someplace. Okay, you're going to have to use your logical indexing to do a database operation on here and get that observation out so that your histogram makes some sense. Because otherwise, if you take things like the average or something like that of the data, well, the average, remember, is not very resilient. When you have outlying data like negative 999.9, you're going to be messing up your average badly. Won't really affect things like medians and modes very much because they're more resilient, but it will affect things like the average. Now, in practice, of course, we could have actually done that trick of figuring out whether there was still any missing data in there or not just by using the min function, and in practice that's what I would do. I would just, before I took an average of anything, I would check to make sure things like, what is the minimum of this data that I'm about to take an average of? If the minimum is negative 999, I haven't gotten rid of all the missing data observations yet. That's a problem. Let me first get rid of it, then I'll check statistics like the average. Okay, this is a powerful set of tools, and part of what you're going to be doing in Project 2 is making histograms of the distribution of temperature as part of how you make descriptive statistics so that you can explain what's going on in a data set. Alright, that's the end of this lecture. There really wasn't anything in this lecture that was easy to ask like a multiple choice question about, so we won't do any questions on this particular lecture. Please let me know if you have any questions. Now just go back and blue line to the main page for this class and move on to the next lecture.